Hi, I'm Chase, and today I am going to demonstrate to you how to solve a how to solve a specific differential equation using a series. Uh, Fun. Okay, so what we have here is we want to solve this differential equation, y prime prime plus 2xy prime plus 2y equals 0. It is a second order linear homogeneous differential equation. I'm not sure what other classifications um, so the first thing you have to know is this is my notation for the series. I find that it is a lot more convenient to write and read as well as to type, of course. I don't know, just the word sum is just the sigmas are kind of hard for me to draw. Um, so what I did here was these are some common formulas for y prime, and y prime prime. I could derive these all from the formula for y that we started with, but I just decided to include them for compactness in my solution. Uh, so for 2y, it's easy to see how we derive that. And for 2x times y prime, well, the power of x just increases by 1, and the constant becomes 2. Now, what you want to do is you want to add these three functions together and set that equation equal to 0. So what I did here was I combine the functions within the three series because they all have the same starting bound, 0. They all three of the all three of the functions have the same starting bound, so you can just combine them. How nice. Now this will give you this inside the parentheses, each power of x to n has to, each constant multiple of x to n has to equal to 0, because you cannot have something times x squared plus something else times x cubed adding up equaling to always equal to 0 unless both of those things were constants were 0. And we don't want just a and we're not looking for it. We're looking for the general solution, which is not going to just be zeros. So because x squared and x cubed are linearly independent. So what we do here is we set this inside of thing equal to 0. This will give us a recurrence relation of c of n plus 2 in terms of c of n. The first two constants, c of 0 and c of 1, are just kind of free. They're just floating around. They can be any constant. And so we'll define the rest of the constants in terms of them. That gives us you can see how I went through the process here. -1, negative 2/3 times c of 1, -1 times c of 0, 1/2 times c of 0, so on and so forth. And so finally, we plug them back in, and we get our series is going to be like c0 plus 1 times x plus -1, and so on and so forth. And here comes the fun part. I actually decided to um to to play around with this one a bit in Mathematica Wolfram language. And so what I did here was to double check that I did the constants right. I used a recurrence table. It is a very helpful function to check that you could do the constants right. And you see the first two constants, C0 and C1, we just set to 1, and then -1 times C0, 2/3 times C1, 1/2 times C0, and so on and so forth. You can check, and that is the same. Now, a weird thing with Mathematica, this would be C of n, but with Mathematica, this is C of 0, but this is actually the item 1 in the list. So we have to say C0, well, you have to add a +1. This should just be C of n times x to n, but it's just a weird Mathematica syntax thing. Now, s is just a variable I made for the scale, and you can plot this thing. How cool is that? And you can zoom out a bit. This weird thing is a differential equation, and you can see if C0 and C1 are both 1, then you actually end up having the y-intercept is 1, and the slope there is 1. You could actually even change the original constants. I haven't done this yet, but and then run everything. Now the original slope is 2. If we set the original initial slope to 0, I wonder what happened. I haven't tried this before. Weird. Some kind of a symmetric function, an even function. Maybe we set this one high. Maybe we set this one to be a y-intercept of 0. Very weird. We get some very weird functions here, but you can, yeah. And it's great with the using the Wolfram language because you can calculate the constants so much farther and so much faster than you ever could by hand. So you can try out this stuff also for free using the Wolfram Cloud. I highly recommend it. Anyways, that concludes solving the differential equation, second order linear homogeneous differential equation using a series. Thanks for watching.